All right. There is a quiz on focus, if I can interest you in that. Doing all right. How are you? All right. Quiz on Quarkus. All right. So we'll see if any more people come in for the next minute, and then we'll start. The quiz is short. The quiz is short. All right. I think we should start. So the question was, how many times does this loop run? So here we're saying for I in range 1 to n, and then we just print I. So the question is, how many iterations? And to remind you, the way this works is this goes from 1 up to n, not including n. So if you go from 1 to 100, but not including 100, that means that you're going from 1 to 99, including 99. That is 99. If you're confused about this, you can think about a smaller number and just figure out what it would be in that case. So if I, for example, say, n is equal to 3, and I'll just fill 3 in here, how many times does this go? Well, from 1 to 3, not including 3, that's 1 and 2. So that's twice. The pattern would be 3 minus 1 if you want to double check. All right. So the answer is 99 times. So this is a little bit different from what would be if we said for I in range n. Again, something like print I, in which case this would be from 0 up to n, not including n. So this would be 0 to 99, and this would be 100 times. And that's because we start from 0 rather than 1, if we say for I in range n. All right. Questions about this? All right. So, okay. So let's, so a few announcements. So there are office hours today at 6 o'clock in SF 1013. The idea is if you want to go to SF 1013 and work on the project, or maybe ask questions between 6 o'clock and 7:30 o'clock today, you can do so. So there will also be office hours tomorrow at a time to be announced, both online, and I'll come into SF 1013 for a while. So late projects. So this was just announced. This is on Piazza. So the general rule is late projects are penalized by 5% per day, rounded up. So if you're late by a minute or you're late by 24 hours, 59 minutes, that is 5% out of a possible 100% that you're penalized by. Everyone starts the semester with 5 grace days, I call those. So you can use up grace days in lieu of being penalized for submitting late. If you submit late by, for example, 1.5 days, you use up 2 grace days, you do not get penalized. Grace days are used up automatically. So you submit the project on Gradescope. If you're late, first grace days are deducted. And then if you run out of grace days, you start getting the 5% penalty. Those are applied individually. If you submit as a team, then it might be that someone loses grace days if they still have grace days left, or it might be that someone loses the 5% per day. Yes. Yes. So the grace days are given to you for all 3 projects. There are 3 projects. You get to use 5 grace days in total. So yes, only for this course. I'm not responsible for any other courses. You can talk to me after class. I have a spare 2 grace days for Civ, that just between the 2 of us. That was a joke to me. Okay. Other questions? All right. So I mentioned this briefly, and I wanted to do this again. You can, if you're writing this kind of test code, it's convenient to write things like this, where you say, I'm printing test 1, and then I have the expected hedons, I have my current hedons, I do my activities, and then I say whether test 1 has passed or not. Here I said test 1 failed, and then I printed out the expected number of hedons, and I also printed out the actual number of hedons that I have. Yes.
What percent of the grade are those words?
Most of it. So there are several hundred hidden test cases that your code would be run with. So the stuff that they give you for free is just a small proportion. And I didn't used to give out any of the code for free, because it used to be that we didn't have Gradescope, and you would just submit the assignment just like you would submit the assignment for any other course. where you do not get any pre-checks. So this is a gift from me to you, by the way. It's not that I'm holding back all the secret ones. It's that I'm giving you the pre-check for free. You should be thankful. Okay. I'm glad I didn't get to laugh because this was that serious. Yes. So the question is, there are several hundreds of test cases, and then what happens if one of those test cases fails? The answer is we test those individually. You get a mark that's proportionate to how many test cases passed, and you do not get penalized if a test case in the middle has failed. Now, the one wrinkle there is that if the test case looks like this, where you do jumping and then resting and then swimming, then if the resting is messed up, or for example, if upper star is messed up in the middle, then of course the entire test case fails because the test case consists of multiple activities. But as much as possible, we separate those out. Okay, other questions? All right, so going back to this example, so here what I'm doing is I'm printing out test one passed or test one failed, and then I'm printing out what was expected and the current heedance. So that looks like this. So if I run this, it says running test one, and then test one passed. I can just make a mistake there. So this is more of a mistake in the test code, which could happen. But if I change it to 14, then it will say good a time as any to try to close this window. Well, this is not okay. This moved. That's good. Okay. Here it says test one failed, and it says expected 14, got 15. If you want to print things out in this format, you don't have to, but it's convenient. You can use, for example, ChatGPT in order to generate this kind of code without having to write it automatically. So here what I've done is I've given it the example of the code. So I said print test one, and then I have my if statement. And then I told it generate test two, where you jump for 13 minutes, expect 13 heathens, and it just generated it. And then I can copy and paste it, and I have my code ready to run. I, of course, still have to verify that the test case is correct, but you don't have to manually type in print test two and stuff like that. There are better ways of doing it once you've had more experience writing code. We are not doing those because they involve all sorts of complications that I don't want to get into. But you can do it like this. I tried to ask ChatGPT for a Python for loop joke. It didn't give me any good ones, so you're not getting any. All right. So, okay. I want to go back to for loops. So to remind you, this is the general mechanism for loops. For I in range, you start with start, you go up to end, not including end, and you go in steps of step. What happens is I starts out as start, and then start plus step, start plus two step, and so on. You go up until end, not including end. The example we ended with last time was computing n factorial, 1 times 2 times 3, and so on. Here's one way to look at how that computation goes. Let's say I want to compute 3 factorial. I'll copy this. Here I have n equals 3. I have result equals 1. And then I first multiply result by 1, then by 2, then by 3, if I want to compute 3 factorial. I start with 1 here because I cannot start with 0. If I start with 0, I multiply result by 0, it will be 0 forever. I go up to, but not including n plus 1, which means up to n, including n. One way to think about it is by what's called unrolling the loop. So what you'll get is I equals 1, and then I equals 2, and then I equals 3. And every time you'll run result times equals I. That means result times equals 1, and then result times equals 2, and then result times equals 3. So if we run this, that's going to happen twice. So if I just run this, I'll get result equals 6, which is what I expect, 1 times 2 times 3. The way it goes is first I is 1. Let me reset result to 1 so that it's literally like that. Result equals 1. Result equals result times 1. Result equals result times 2. Result equals result times 3. Make sense? All right. So that is called unrolling the loop. It sometimes has applications if you are trying to really optimize things and the mechanism, the machinery behind the for loop, you don't want to spend compute resources on doing that. Sometimes unrolling the loop is more efficient. This would not come up unless you are doing hardware development. You should do the for loop. And of course, the advantage of having the for loop is that here I had to specifically say I equals 3. It's not going to be n factorial for an arbitrary n. If I unroll it, it's going to be for fixed n. Let's do another example. So let's say that what I want to do is check whether the number n is prime or not. So a number is prime if it doesn't have any factors that are smaller than itself and greater than 1. We have a mechanism for checking whether a number is divisible by a factor or not. We can compute n mod m and check whether n mod m is equal to 0. Right? If you remember, n mod m is the remainder of the division of n by m. If the remainder is non-zero, that means that n is not evenly divisible by the number m. Does that make sense? Questions? So the simplest possible thing you can do in order to check whether a number is prime or not is to just check whether it's divisible by 2, whether it's divisible by 3, whether it's divisible by 4, and so on, up until n minus 1. And if you find that it wasn't divisible by any of those, then it's got to be prime. The one exception to this is 2, which is in fact divisible by 2, so that's a special case. Let's do that. So I encourage you to write this along with me. This is one of those situations where you want to actually have the experience of having typed it in. Two is a prime number. I'll treat it as a special case. I'll just say if n is equal to 2, then it's prime. I return true right away. If you remember, return true means that that's the last thing that the function does. It just returns true. Otherwise, I'll try to divide by every possible m. So I'll say for m in range n, and starting with 2, I want to check whether n is divisible by m. So why do I start with 2 and not, let's say, just say for m in range n? Anyone? Yes. Yes, every single number is divisible by 1, and also every single number, you cannot try to divide it by 0. So you definitely cannot start with trying to divide by 0, because if you try something like 5 mod 0, it will complain, you cannot try to divide by 0, there is no such thing as a remainder. Yes. 2 could work because the number could be even. So if n is equal to 10, I do want to try to divide it by 2. Okay. Other questions? Yes. So 2 is included, it's n that's not included. So m is going to be 2 and then 3 and then 4 and so on up until n minus 1. So the last thing is not included, the first thing is included. Yes.
Go up so n not n plus 1 we can become that, and then there would be a prime number divisible by itself.
So not exactly that. So the question was, why do we go up until but not including n? And the answer is n is always divisible by n. And the setup here is you try to divide by every plausible factor m. You don't want to try to divide n by itself because it's always going to be divisible by itself. That's not going to say anything. And in fact, it's going to be misleading because what I'm about to say is that if n is evenly divisible by m, so if n mod m is equal to 0, we found a factor of n, so that means that n is not prime. And that means that I'll return false. If I tried dividing n by every possible m, and I never returned false, then I'll return true. So let me first show how this code runs, and then we'll talk about the structure of the if statement. Five, for example, is a prime number. I'll put a breakpoint here. I'll step in. 5 is not equal to 2. Now m is going to start out at 2. And we're going to check, is n mod m equal to 0? No. So 5 mod 2 is 1. Makes sense. 5 is an odd number. So we won't return false. And now m is going to be 3. Is 5 mod 3 equal to 0? No. I can check what 5 mod 3 is. Five mod 4? No. And now we're done. We tried m equals to 2 and 3 and 4. We never returned false. So we get to line 11 where we return true. If I say print is prime, it will print true. On the other hand, if I try is prime 4, the answer is going to be 4 is not a prime number because 4 is divisible by 2. The way it would work, again, put in a breakpoint, step in. The first divisor we try is 2. And 4 mod 2 is equal to 0. So that means that we get to line 9. So that means that is prime 4 is going to be false. Nothing else is going to happen. And it's going to print false. The value of is prime 4 is false. One common thing that people are tempted to do is to say, else return true. Does anyone see why that would not work? Yeah. Green shirt. Yeah. Yeah.
Like if, for example, your number is like 3 and it does not equal 0 the first time you run through, it will just return.
Yeah, that's exactly right. If we're trying is prime 4, that would actually work because we'll return false right away. But if we try something like is prime 25, that's not prime. However, step in. The first thing we try is if 25 mod 2 equal to 0, it's not. So we get to return true. So that doesn't make sense. 25 is not prime, even though it's not divisible by 2. Yes. Yeah. There's several. You could also do it in steps of 2, stuff like that. Yeah. We'll get to your question. So does this make sense? So this doesn't work. So the deep reason this doesn't work is that you only need to find one counterexample where the factor does divide the number for the number to not be prime. However, for the number to be prime, you need to check every possible factor. Yeah.
And less than 2?
In principle, so the question was, what if n is smaller than 2? And the answer is, well, what if n is a float? What if n is a string? So at some point, you need to put an end to those kinds of questions. Here, we just assumed that n is a positive integer. You're right that in principle, you might like to account for different types of inputs. In Python, you do not usually do it because in Python, there's not a straightforward way to enforce all sorts of limitations that are not about, is it negative? Okay. So questions about this? Okay. All right, moving on. Oh, sorry. So there was a question before. Yes, you are right. You do not have to go up to n-1. So what the person pointed out, there are all sorts of optimizations here. What the person pointed out is that if n is factor 1 times factor 2, then 1 of f1 or f2 is smaller than square root of n or equal. Right? Because if they're both larger than square root of n, then the product must be larger than n, and that can't be because f1 times f2 is supposed to be equal n. That means that you could go up to square root of n, not up to n. Also, you could say, I'm not going to do it now. There is no point in trying to divide by 2 and then 4 and then 6 and then 8 and so on, because if the number is not even, it's definitely not divisible by 4. You could try to divide by 2 and then go up in steps of 2. But also, this is not an efficient algorithm in the first place. This was just for the sake of the example. There are much more efficient ways of doing formality testing. Okay. Other questions? So that was just in response to a question. All right. I want to do a fun kind of example with a for loop. I'm going to try to compute pi. So here is a way to compute pi without doing anything that's too complicated. You could think about the square that goes from 0, 0 up to 1, 1. And then I'm going to do it on a computer, but you could well imagine just picking random points and then asking how many of the random points are inside the quarter circle compared to the total number of random points that you put on this square that's of area 1. And then you can compute the ratio of the number of points inside the quarter circle to the total number of points in the square. And that number is going to be 1/4 pi. Why? Because the area of the quarter circle is 1/4 pi 1 squared, right? Because the area of the entire circle is pi times 1 squared. So the area of the quarter circle is 1/4 pi times 1 squared, so 1/4 pi. So that means that the ratio of the number of points inside the quarter circle, that's AM in this notation, to the total number of points in the entire square, that's AN is this notation, is going to be 1/4 pi, because that's the ratio of the area of the quarter circle to the area of the square. Questions about this? Does that make sense as an idea? Okay. So I can get random points using the random function in Python. So if I import random, I can say random.random, and I'll get a random number between 0 and 1. Yes.
Like, is it actually randomized or like
It's not actually random. It is, we'll talk about random number generation another time. You're right to point out that the computer is deterministic, so it must have been predetermined what that number is. But effectively, this is random. All right. So the plan is generate n random point. In the notation here, this would be an random points. Keep track of am, the number of points inside the quarter circle. And then compute 4 times am divided by an. The idea is that if you generate enough random points, 4 times am divided by an is going to be approximately pi. Let's try to help a function. I want to return true if xy is a coordinate inside the unit circle. How do you do that? If you have a coordinate xy, yes. Yeah, that's exactly right. So xy, a point over here, is inside the unit circle if the distance from xy to 0, 0 is smaller than 1. Right? So that's exactly what you said. X squared plus y squared is smaller than 1. The square distance smaller than 1, that's the same as the distance being smaller than 1. Or write it out explicitly. And I'll return r squared smaller than 1. That is going to be true if the coordinates xy are inside the unit circle. It's going to be false if it's not inside the unit circle. Now what I'm going to do is generate n random coordinates, pairs of coordinates, and check for everyone whether the coordinate is inside or out or not inside the unit circle. AM initially is going to be 0. And I'm just going to repeat this n times. X is going to be a random number, and Y is going to be a random number. And if XY inside if this is true, I'm going to increment AM by 1. Does that make sense? I could have said inside unit circle equals true, but that would be superfluous, right? AM plus equals 1 is going to happen if the coordinate xy is inside the circle. Once this is done, I can compute 4 times the ratio of AM to N. If I wanted to align this, I could have said AN equals N, but not going to do it. Yes. That would be the number of the random points here. Obviously, if you have one random point, the estimates are going to be either 0 or 4. If you have more points, the hope is that you'll get more and more accurate estimates, precise rather, estimates of pi. Say again? Yeah, so that's an input to the function. So we'll try it in a second. Yes. Yes, the number of random points. Let's try it. Print. Let's try it with 1000. Of course, it's going to be different every time. Here, it estimated it to 3.056. I ran it another time, so now it estimates it to 3.152. Those are random numbers. Add two zeros here. That's going to be slower, but it's going to give a more precise estimate. Let's add another zero. At this point, you saw that I needed to wait. It's going to be harder and harder to estimate digits that are further and further away. I think we can afford to wait this much. I think it's going to take a few seconds. And here it got the fourth digit right as well. Of course, you might argue, well, maybe I got lucky. Okay. Questions about this? Yeah.
Can you explain why is that ratio?
Yes. So the question was, why is this ratio? So again, what are we doing here? We are throwing random numbers inside this square and random coordinates. We are then asking how many of the coordinates are inside the unit circle over what is the total number of coordinates. And what I'm saying is that the ratio of the counts of points inside the unit circle to points in the square is the same as the ratio of the area of the unit circle to the square. The area of the quarter circle is 1/4 pi. The area of the 1/1 square is 1. That means that the ratio is 1/4 pi. Multiplied by 4, that's going to be pi. Does that make sense? Right. Other questions? Yeah.
Like a test or midterm, how many zeros would you expect to flip, or does it not matter?
So it doesn't really, there are ways of estimating how many zeros you need in order to get a particular precision, but this is way beyond the scope of this course. Okay. Other questions? All right. I'll just run it again. We'll see. Okay, I'll add another zero and we'll check in on it at the end of the lecture. So, oops. I want to start talking about while loops. A while loop is, again, a way to repeat a block of code multiple times. Unlike a for loop, where you tell it how many times to repeat the block, what the while loop does is say, keep checking the condition and keep repeating the block while the condition is true. Let's do the simplest. While loops are generally trickier than for loops because with a for loop, you just tell it how many times to repeat. While loop keeps checking the condition, so you don't know ahead of time how many times it's going to repeat. But we can implement basically a for loop using a while loop. And I think that's the easiest way to think about while loops in the beginning, at least. Oh, it's done. So what I want to do is I want to implement this, but using a while loop. Here's how I can do it. I can say I is equal to 5. And then I'll say while I is smaller than 10, I'll say print I. And then I'll say I plus equals 1. So let's think about what this does. Spoiler, it does this. initially I is equal to 5. So initially it'll print 5. And I is 5. Then I is going to become 6. It's going to check, is 6 smaller than 10? Yes, it is. So it'll print 6. At this point, I is 6. It's going to check, is 6 smaller than 10? Sorry. And then it's 7. So is 7 smaller than 10? Yes, it is. Print 7, make I 8. So I is going to become 7 and we'll print 7. And then I is going to become 8 and we'll print 8. And then I is going to become 9. So over here, I becomes 9. We print 9. Okay. One last thing. Unlike with a for loop where you can know that this is going to be 5, 6, 7, 8, 9, 5 times. With a while loop, you don't necessarily know how many times exactly the iteration is going to repeat. You might have something like this. While 8 is greater than 7, print. What's the lecture at 5 o'clock? Is it calculus? It's Civ. So it's going to be Civ forever because 8 is greater than 7. Always that doesn't change, unlike I smaller than 10, which does change. Hence the classic joke. So on shampoo bottles, I actually checked. It doesn't usually say it, but it sometimes says instructions, lather, rinse, repeat. So why did the programmer stay in the shower forever? Because there was an infinite loop on the shampoo bottle that says lather, rinse, repeat, something like this. It's kind of like, why did the Anxi stay in the Civ lecture forever? All right, I will see you next time. No, you're not.
For the project, for like the most fun activity like this, if ever like two, let's say two like activities return the same amount, do I return one of them or like?
That doesn't actually happen, but you can the official answer is you can return one of them,
Oh, okay.
but it did not come. But
Oh,
yeah.
Yeah, I'm just not sure if resting count for 0 and.
No, it does not come.
Oh, that's okay.
Yeah.
Are you marking our like